Thank you so much for having me. I also want to thank Khalid Dumaldi. He was very enthusiastic about this and trying to, coordinate all of this with me. So thank you so much. Before I start, I want to say that the SEDS initiative is such a great thing. And I'm very proud of y'all for promoting knowledge about space and astronomy in Sri Lanka, because I know that Sri Lankans, we can do this really well. Like, we have the knowledge to do it. We just need to begin somewhere, and having this kind of initiative is amazing. Okay, so without further ado, I will talk to you all about black holes. So, සිංහලෙන් මෙවට කියන්නේ කළු කුහර කියලානේ. අද අපි ඒවා ගැන පොඩ්ඩක් හොයාගනිමු. So, I'll start by talking to you about how black holes, are formed in the universe. So let's go with that. Can you see my slides? Can you see them moving? I hope so. Okay, so let's start by this. How do stars form in the Milky Way? So stars, they usually form in these star-forming nebulae. So there are two pathways. There are stars like our sun, and stars that are much, much, much more massive than our sun. So what happens to a star like our sun? So once it's born, it's called a protostar, and then it evolves into something like our sun. And then after billions of years, it expands and becomes a red giant. And after it becomes a red giant, it, expels its outer atmosphere, and it creates these things called planetary nebulae. And these are very beautiful. I'm sure you've seen pictures of these all over the internet. They're really beautiful. And in the middle of these planetary nebulae, you get white dwarfs. So white dwarfs are very hot cores of these stars that are left behind, but they're not really black holes. They're not interesting when it comes to what we're going to talk about today. So how are black holes formed? So black holes are formed from stars that are much, much more massive than our sun. So when we talk about the mass, it's about how much it weighs. And for black holes to form, the stars have to be more than about 8 times the mass of the sun. So what happens to these big stars? So what happens to these big stars is, after they're born, they evolve into red supergiants. Not red giants, but red supergiants. So they are really big. And after they become red supergiants, after a little while, they go through the supernova explosions. So these supernova explosions are really energetic, really bright, and they create so much light. And after the supernova explosions, you get either a neutron star or a black hole. And how do you know which one is the ultimate fate of a star? It depends on how massive the star is in the beginning. So really massive stars, about more than about 30 times the mass of the sun, they will form black holes. So that is the formation path for black holes in the Milky Way. Massive stars, they evolve to red supergiants, and then they become a supernova explosion, and then they create black holes. Okay, so how do astronomers look at stars? So I'm just giving a background knowledge about astronomy here. So we look at this diagram called the Hertzsprung-Russell or HR diagram. So what is shown here is the luminosity, the brightness of the star, and the temperature, the surface temperature, how hot the star is. So you can see that all the stars, they form a very nice sequence. So what we call this is the main sequence. So the sun is about here. The temperature of the sun is about 5,800 Kelvin. And then you can see that stars like our sun, they become red giants. And then more massive stars, they're really hot. They're like 30,000 degrees Celsius, really hot stars. And they're very bright. They're like almost 1,000,000 times brighter than our sun. So they become supergiants. and then they become black holes. So white dwarfs are clustered around this part of the diagram. So this diagram is what we use to study stars. This is called the HR diagram, and it's good to know that there's a nice sequence of stars that you can tell. You can understand where the stars are at in their lives by looking at this diagram. Okay, so as I said, massive stars are what forms black holes, and that's why we want to study and understand them. But unfortunately, unlike the sun, massive stars die in a million or tens of millions of years. They don't live long, so they are born, and the next thing you know, they die. So they have very short lives, but even in those short lives, they create so much matter, and they really change the environment around them. So this is a really cool picture that I wanted to show about massive stars doing weird things. So on the left, you can see a massive star in a galaxy NGC 6946, and this was taken in 2007. And then the Hubble Space Telescope went and looked at the same place in 2015, and the star is not there anymore. So what happened to the star? So it was there in 2007, and it was not there in 2015. So what we think happened is that the massive star collapsed on itself, it died, and made a black hole. So in this circle you see here, there's a black hole there somewhere, but we can't see it because black holes don't emit any light. So this is like one of the most nicest examples of how you can see a black hole being formed. And this is not in the Milky Way, but in a different galaxy. Okay, so what happens to massive stars just before they die? So stars when they are born, they have hydrogen, a little bit of helium, and some other elements like magnesium, carbon, etc. So stars, how they produce light is by fusing hydrogen to helium. So that's what our sun is doing right now too. It has hydrogen, and it fuses it into helium in the core. So massive stars, since they're so big and so hot, they can go beyond that. So first they transform hydrogen to helium, and since the pressure and the temperature at the core is so high, they can transform helium to carbon, and then carbon to neon, neon to oxygen, so forth, until it reaches iron. So it goes through various nuclear fusion cycles until you get iron in the middle of the star. So that's where everything goes wrong and everything stops, because after you make iron in the core, you can't make anything else. So iron is the final element that you can make through nuclear fusion. So the analogy that we like to use to look at massive stars is that it's like an onion. So you have different layers. You have hydrogen, helium, carbon, neon, oxygen, silicon, and then iron in the middle. So once you have iron in the middle, since you can't go through nuclear fusion in the middle, the star starts to collapse in on itself. It starts to die once you make iron. So once it does this collapse, you have the so-called supernova explosions, which are really beautiful, and we are in a really good era to study these supernova explosions these days. Okay, so here I've shown a plot again from a different galaxy, NGC 2403, and there's a star cluster in this galaxy, and you can see a star shown by this arrow. And then in 2004, one of the stars, it went through a supernova explosion, and it created so much light. So you can see it was like faint before but very bright after the supernova explosion. So these massive stars, they will always die as supernova explosions, but it's a little complicated. Like if you create black holes, sometimes they can die without a supernova explosion too. The physics is still very uncertain. As we already said, we don't understand this very well. We're still trying to figure it out. Okay, so now we come to the Milky Way. how many supernova explosions go off in the Milky Way. So based on our current understanding, we think that there are 2 supernova explosions. Oh, sorry, this is per century, not year. 2 supernova explosions per 100 years. So one every 50 years. But we cannot see all of them because this is like a artist's illustration of the Milky Way. The sun is around the outer edges of the galaxy, and if you look towards the center of the galaxy, there's so much dust. So sometimes we will not see the supernova explosions because there's so much dust covering them. But the last supernova explosion that we saw, that humans saw, was in 1604, like about 400 years ago. The Kepler supernova explosion. But hopefully we will see one very soon. If one happens every 50 years, we should see one, hopefully, in our lifetime. So that's my goal, to see a supernova explosion in the Milky Way. Okay, so what happens after a supernova explosion? So they leave behind these beautiful remnants. So these are supernova remnants. They're like planetary nebulae, but not really, because what happens is when the supernova goes off, it just like rips apart everything around it because there's so much energy. It's like a bomb going off, and that creates all of these beautiful elements. It creates heavy elements. So supernova explosions really add so much to the galaxy. The elements that are in our body, they are formed through supernova explosions. So these are 3 examples of supernova remnants in the Milky Way. So this is one end product of the supernova. But what about the core? The core, as I said before, it collapses. So in the middle of these remnants, you have either neutron stars or black holes. Okay. So there are a lot of black holes and neutron stars in the Milky Way. So we think that there are about 100 million black holes that are in the Milky Way. 100 million, that's a lot. And about 1 billion neutron stars in the Milky Way. So what about the sizes of these compact objects like neutron stars and black holes? So this is an image from, it's a very old image, but it's like Google Maps looking from the satellite wave at New York. And you can see that the neutron stars, typically their radius is about 10 kilometers. So it's not that big, but it's so dense. There's so much matter within that 10 kilometers. So that's why they're like very exotic or very unique. Black holes are even more dense, and they have, and as I said, I will explain it a little later. In the center, they have a singularity. So their radius, we use a Schwarzschild radius. That's what we use to calculate the size of the black hole. It's about 5 kilometers. So much smaller than a neutron star. Okay, so what is a black hole? So so the definition, if you go to Wikipedia, is so black hole is a region of space-time where gravity is so strong. So gravity is really strong that nothing, not even light, can escape the black hole. So if you go beyond the event horizon, that is it. You can't come back. You will fall into the black hole. So the most famous equation that we use to characterize black hole is the so-called Schwarzschild radius. It's a very simple equation, 2gm/c². C is the speed of light. And that tells you about the event horizon in the black hole. So this is something that's always used to, when it comes to, if you want to know the size of a black hole, you use this. Okay. So how many different types of black holes are there? So that is a great question that we are trying to answer. But so our understanding right now, there are 4 types. You have primordial or micro black holes, and then you have stellar mass black holes, then you have intermediate mass black holes, and then you have supermassive black holes. So primordial or micro black holes, they are very small, and the mass, the amount of matter that's contained in the black hole is about that of the moon. So it's very tiny. People think that they were created right around the time of the Big Bang, and people are trying to find them, but we have not have good evidence for primordial or micro black holes yet. So the only two types that we have very good observational evidence are stellar mass black holes and supermassive black holes. So stellar mass black holes, they are the ones that are formed after supernova explosions, after stars die and collapse to create stellar mass black holes. Then intermediate mass black holes, we are still not sure if they actually even exist, but theory predicts that you can find these, but we haven't found them yet. And then supermassive black holes. These are the giant, massive black holes that you have in the center of every galaxy. So every big galaxy has a supermassive black hole. I will talk to you about it a little more. I'll show you some images also, which is kind of cool. Okay, so there are 4 types of black holes. Okay, now how does a black hole look like? What is the anatomy of a black hole? Like if you want to dissect a black hole and look at it, this is a great figure to do that. So there are certain characteristics that we'll go through. So you have, and the easiest thing to start with is the accretion disk. So what is an accretion disk? So you have a black hole, and then the black hole has so much gravity, it really is a very unique object, and it bends space-time so much that matter can fall into it. So what happens is matter around the black hole will come into a disk. So it forms an accretion disk, and in the accretion disk, since the gravity is so strong, everything gets heated up. It's like you are cooking something, like making a roti. So it's really, really hot, and it creates X-rays, optical light, infrared light, it creates all sorts of light. And then you have the so-called event horizon. So event horizon, that is the radius at which nothing can escape. So if you go beyond the event horizon, you can't come back. So that is a point of no return. So you should not try to go anywhere near that. And then you have the photon sphere. This is a very important characteristic. So what happens is, as I said, there's an accretion disk, and it makes light because it's heated up. And then this light is created by, it's composed of photons. So photons equal light. So all the photons, what happens to the photons once they are made? So since again, gravity is so strong, space-time is bent at the black hole. So instead of a straight line for the light to go through, it goes through curved space-time. So it creates something called a photon sphere. It's like a ring, and you can kind of see it in the next slide, where I will talk to you about actual pictures of black holes. Okay. So then you have these things called jets. So you have, again, matter from the accretion disk. Sometimes it gets, thrown out of the black hole in jets. So they're very fast, like almost near the speed of light. Things get just thrown out from the black hole in these jets. And you see these jets in like radio observations. So they're very interesting features of black holes. And then the innermost circular, the stable orbit is the last orbit around a black hole where you can, somehow escape. Beyond that, you cannot actually have any orbit that leaves the black hole. Everything goes into the singularity. And yeah, the singularity is the final point. So at the very center of the black hole, you have something called a singularity. So what happens there is that matter has collapsed so much to form something with infinite density. So it's like space-time is ripped apart, and that's what the singularity is. So to study this, you need to know general relativity. That's what really describes black holes. I will not go into it in the talk today, but I will talk to you about how astronomers study black holes. Okay, so this is one of the most coolest and really amazing pictures that I've seen. This is the first picture of a black hole, and this was taken from the Event Horizon Telescope in 2019. So 2 years ago, humans created the first picture of a black hole. This is amazing. So what you see here, this kind of ring, is the photon sphere created by the accretion disk. and in the middle you see, there's a kind of dark patch, and we think that's where the singularity is, where the event horizon is. So again, this is kind of amazing that we were able to do this. This is the supermassive black hole in another galaxy called M87, and we are looking at a black hole, and we can see the features that I showed before. The photon sphere, you can see the event horizon. It's amazing, and we are actually trying to do this for the Milky Way galaxy too, to make a picture of the Milky Way's black hole in the center. They're still working on it, but I think it should come out in the next few years. We'll be able to see our own Milky Way's black hole. So stay tuned for that. So the way that the picture was made was kind of amazing. So there were a lot of telescopes all over the world that had to do this in tandem. So what they did was they were observing this black hole from all of these telescopes at the same time. There's a really crazy big effort to do this. You have to coordinate all of the different telescopes and observe the same black hole, and then collect the data and analyze it. So the actual data was taken in 2017, and it took them 2 years to actually, collect the data, process it, analyze it. So it took a long time to do this. So it's not easy at all. But thanks to the efforts of these scientists, we were able to see a black hole for the first time. Okay, so going over supermassive black holes, there are lots of different kinds of supermassive black holes. Like the sizes of these supermassive black holes are very big, but they are also different for different galaxies. So some galaxies have very small supermassive black holes, some have really big ones. So black holes come in all shapes and sizes. Like you can't, say every black hole is this size. It depends on how much matter there is. So supermassive black holes can have million to a billion times the mass of the sun. So like you can fit a billion suns into that black hole, which is kind of crazy. Okay, so now we will take a look at the black hole in the center of the Milky Way. Can you see this? Okay, yeah, okay. So this plot that I'm showing is the orbits of stars in the center of our galaxy. So you can see that the stars have different orbits, but they're all orbiting something in the middle of the galaxy. So through general relativity, we did the calculations, people did the math, and what they're finding is that there's a very big black hole in the center of the Milky Way. This is actual data that we're looking at. So this is from 1995. People have been observing this from 1995 to 2020, and to look at the orbits. So the orbits take years to actually look at. So looking at this, we know that there's a big black hole in the center of the Milky Way. Okay. So this is another image of the same thing. On the left, you can see the current data, the current quality of the data. We have something cool called adaptive optics that we can use to focus the telescope very sharply to get good data. But technology gets better. And then on the middle, you can see what will happen with the next generation, the next development in adaptive optics. The resolution gets much better. And then we are building 30-meter telescopes, 30-meter class telescopes, huge telescopes. And with those telescopes, we'll be able to see it even at higher resolution and study the black hole even better. So better data means we can understand the system better. Okay, so the next part of my talk is how do we find these stellar mass black holes? So that's what we're going to try and understand. Okay, so this is a artist's illustration of what a stellar mass black hole looks like. Again, you can see the accretion disk, you can see the photon sphere, you can see the event horizon and the singularity. Like it's all shown here. So the photon sphere shows up like a ring kind of thing. So you've seen this in the movies. Interstellar had a really nice black hole there. So that's all realistic. So the part of the movie where they actually go inside the black hole, that's not real, but the image of the black hole, that's very real. Okay, so black holes and neutron stars are typically like very hard to find. Why is that? Because they don't make any light unless you have an accretion disk. Some of the black holes don't have accretion disks, some do. So there are some kinds of black holes that are very easy to find. So I will talk to you about the easy black holes first. So these are from some things called X-ray binaries, and then we have gravitational waves. So I will talk to you about those two in the next few minutes. So let's talk about X-ray binaries. This is an image of an X-ray binary. It's an artist illustration. It's not an actual image. It's just some artist drew this diagram, and then we're going to understand what they are. So what is an X-ray binary? So a binary star system is essentially you have two stars orbiting around each other. So you have, in an X-ray binary, you have a black hole or a neutron star in the center, and then you have another star outside it. And then what happens is that the black hole is eating matter from the companion star. So it just starts sucking out matter from the star, and it creates an accretion disk. So you can see the matter flowing out from the star. It will eventually eat most of it, so it just keeps eating, and then there's an accretion disk that where all of the matter falls into, and then it goes to the black hole, and the black hole becomes bigger, and you have these jets, the relativistic jets that I told you about. They just throw things out of the black hole because of how hot it is and how how strong the gravity is. So this is the structure of the X-ray binary. You have the star, and the star is losing mass. So things go from the star to the black hole, and you have these things called hotspots where the matter just flows into the accretion disk. And this system, it creates a lot of X-rays. So X-rays we use to study our bones when they're broken, fractures, things like that. But X-ray binaries are systems that create so much X-rays. So if you have X-ray telescopes in space, like Chandra, you can look at the sky and find these systems because they make so much X-rays. That is how we find them. That's why they're called X-ray binaries. So a lot of X-rays, and they're very interesting systems because you can understand how black holes eat matter and how they evolve. Okay, so that's one kind of system. Now the other type is gravitational wave mergers, and these were discovered by Ligo and Virgo. So I will talk to you about Ligo and Virgo in the beginning, and then go describe what they are. So these are actual pictures of the Ligo Virgo gravitational wave observatories. So what you see is there are it's like a shape, like an L-shaped observatory. It's an interferometer. I will describe what it is in the next slide. But each of these arms is about 4 kilometers. 4 kilometers times 4 kilometers. It's huge. So there are 3 of these. There are 2 in the United States and 1 in Europe. So they are currently not working right now because they are going through maintenance, but they will start working again very soon. That's the hope. So how do these detectors work? Okay, so why we made these detectors is to try and study gravitational waves. And gravitational waves are created when black holes merge. So there are 2 black holes and they merge to form one black hole. And when it happens, they create ripples in space-time. So it's like you put a rock in water and then you see the ripples come out. So, but instead of water, this is actual space-time. So what happens is you have a laser, and then you have these 2 L-shaped arms, and then you send the laser to a beam splitter, and then that splits the beam into 2. So you have one beam going in one direction and the other beam in the other direction. And then at the end of the detector, you have a mirror. So it bounces the signal from the laser back into a detector, so we can measure it. And then based on that, we know we know the speed of light, and then we can calculate the distance that the light traveled. So the distance should be 4 kilometers. But when there's a gravitational wave, it creates ripples in space-time, and that like extends the length that the light has to travel to. So if there's a gravitational wave, this 4 kilometers will not be 4 kilometers. It will be slightly bigger or smaller than that. And we can actually measure that difference and calculate, gravitational wave signatures. That is how LIGO works, and it's been working well. The first gravitational wave was detected in 2015, and since then we've been finding more and more and more of these gravitational wave mergers. Okay, so this is what an artist illustration of gravitational mergers look like. On the left, you have two black holes. They're orbiting and then they merge to create one big black hole. On the right, you have two neutron stars. So these neutron stars are also orbiting around each other, and eventually they will merge. But also you could have a black hole plus a neutron star. There are different combinations that you can have. It doesn't have to be of the same kind. And we have evidence of a black hole neutron star merger also. So yeah, these are very cool events. And this is again real data from one really awesome event that we found in 2017. So this is the merger of two neutron stars. So two neutron stars merged, and so when black holes merge, they don't make any light. But when neutron stars merge, they make light. So you're looking at this galaxy, and then you see this kind of spot here, and what happens is that was because of the neutron star merger. It made so much light, and we were able to see it. And this on the left, you see what the gravitational wave looks like. This is real data from LIGO Virgo. It's like a small signal. Like if you look at it, you can see like a kind of streak there. That is the actual gravitational wave signal. So using these signals, we can study the size of the black holes, what they were before and what they are after the merger. So what happens is, so you have two black holes, and then you add them up, and there's some mass that's lost because of the gravitational waves. So it's not really 1 + 1 = 2. It's like 1 + 1 = 1.5, something like that. So it creates a bigger black hole, and we think this is how bigger black holes are formed. So two black holes makes another black hole. That's what happens. Okay, so this is a very popular plot that's shown in this field. So it shows the size of the black hole compared to the sun. So you have neutron stars in the bottom, and then you have black holes on the top. So these are all from LIGO and Virgo, and then the purple ones are from X-ray binaries. So you can see that there are so many black holes that we discovered, but the black holes from LIGO, Virgo, they're not in the Milky Way. So how do we find black holes in the Milky Way? So the problem is, so compact objects like black holes in X-ray binaries and gravitational waves, they are like the tip of the iceberg. They are only a small number, but there are so many non-interacting black holes. That's what we call them, non-interacting black holes that are not discovered yet. It's like when you look at the iceberg from the sea, you have things that ones that pop out outside the water, and then most of the iceberg is below the water. So there are a lot of black holes that we haven't found yet because they don't make X-rays, they don't make gravitational waves. We can't find them because they are very dark. So new advancements in the field are letting us study them. That's what I'm going to talk about, how my research is enabling us to find the bottom of the iceberg of black holes. So they are very hard to find, as I said, and we have to look at new techniques in the field to find these black holes. How do we do that? So yeah, so they exist. We know that they exist, but it's so hard to find them. So to find them, we try to find black holes orbiting around other stars in the Milky Way. So this is an illustration of binary orbits. So you have one star and another star in this, but we're trying to find one star plus one black hole. They are orbiting around each other, and that is the way to find black holes in the Milky Way. Okay. All right. So binary orbits are what we are trying to look at. So when we look at the sky, there are stars, and actually 50%, like more than half of all the stars are in binaries. Our sun is not in a binary, but it's unusual because most stars are in binaries. So we can look at these systems and do analysis to find out various parameters like the orbital period, inclination, things like that. So this is how a binary orbit looks like in the sky. This is kind of advanced, but I will not go talk too much about it, but this is the technique. We're looking at binary orbits to find black holes. So there are three methods to find black holes in the Milky Way. One is the radial velocity method, and then the second one is the photometry method, and the third one is the astrometry method. So I will talk to you about the radial velocity method and the photometry method. Okay, so this is the summary, but let's go into detail about the radial velocity method. Okay, so what is the radial velocity method? So you have a star on the left. If you look at the left figure, you have a star, and the star makes light. So what happens if you send the star's light through a prism? So you send it through an instrument with the prism, and it splits the light into this something called a spectrum. So that is the basic idea. We use spectroscopy. So you have starlight, you split it, and you get a spectrum. It's like, you know, when you look at a light source with this prism, you have a rainbow. So essentially, we are looking at the rainbow of a star. And it's not a feature like this, but you have things called absorption lines. Absorption lines are there because the star has elements like iron, carbon, nitrogen. There's a lot of elements inside the star and the atmosphere. So those elements, they absorb the light, and they have so-called spectral lines or absorption lines. So if the star is stationary at zero velocity, they will all be at the same velocity on Earth. So what we do is we look at the lines on Earth, but when we look at the lines in the star in space, they are not in the same positions. This is because of the Doppler effect. So what happens is the stars are moving in orbits. So when the star is moving, the lines of the star is also moved because of the Doppler effect. So it's called redshift, blue shift. And I think you might have heard of this technique before, but this is being used to study exoplanets. But we are now using this to study black holes. So in this figure, it's about a star and an exoplanet. So you have a star and you have an exoplanet here. So the star goes on an orbit, it goes on a circular orbit here. And if the star is coming towards us, then the lines are blue shifted. If the stars are moving away from us, the lines are red shifted. So that's what red shift and blue shift is. And we can look at the lines and compare it with what we know on Earth it should be. So we have techniques to do that, to compare. And then what we get from doing this is you get a velocity. So this is the plot that explains the radial velocity method. So you have speed on the y-axis, and then you have the time or how many days on the x-axis. So you can see there are two stars, the star and exoplanet here. And then as the star is moving on the right, you can see how the lines also get red shifted and blue shifted. So they keep moving. And then we calculate the velocity of the star from the lines, from the Doppler effect. So that's what you see. You have, for a circular orbit, you have a sine curve. You get a sine curve and you can look at the data. You see the star keeps moving in their orbit. That is the basic idea. We look at the Doppler effect to calculate the velocity of the star. So what we have, again, this is a plot showing Doppler spectroscopy. You have the data. You look at the star many times. You keep looking at the star and you get data. So you keep getting data and you make a nice plot. And you can calculate the amplitude of the sine curve. So sine curves we use, it's a very common thing in math. So we can calculate the amplitude of this, which we call K. And then we can calculate the period also, because if you look at this diagram, it's the same thing. It keeps going around the same orbit over and over again. So it repeats. So we can calculate a period. And once we have a period, you can calculate a lot of things about the star and the binary. We can calculate the eccentricity, that's, if it's an elliptical orbit or a circular orbit. And the most important thing for us, the amplitude K tells us about the mass of the black hole. So you can use that to guess if what we are seeing is a black hole or not. So bigger amplitudes mean that it could be a black hole. So bigger the K, the better it is for black hole searches. For exoplanets, this velocity K is about meters per second amplitude. For black holes, it's about tens of kilometers per second. It's a big number. Okay, so the modern field of astronomy, there are surveys called spectroscopic surveys that look at stars all over the Milky Way, and they do this Doppler spectroscopy many times. So there are about 10 million Milky Way stars that are being monitored right now. And this shows you how the actual data looks like. So on the top, you have a very hot star, and on the bottom, you have a very cold M dwarf, so it's a red dwarf. And then the star that's closest to the sun is the G dwarf in yellow. So we get spectra. So that's what we do. We get spectroscopy of stars, and then we calculate the Doppler effect. Based on the Doppler effect, we can tell if there is a black hole or not. Okay, so the next technique is called photometric method, or the photometric variability method. So let me explain what this is. So we can monitor the entire sky and record the brightness of every star. We can measure the brightness and look at how it changes with time. So you take a picture of the sky every few days, measure the brightness of every star, and look at how it changes with time. So what I'm showing here is something called a light curve. A light curve is basically brightness of the star against time. Brightness on the y-axis, time on the x-axis. So here I'm showing something called an eclipse in binary. You have two stars, both of them have light, and you can see that when one star comes in front of the other, it blocks some of the light from the other star, and it creates a dip, or what we call an eclipse. So it's like the solar eclipse, but you can actually look at other systems in space. And then when one of the other stars goes behind the other, again you block some of the light and you will see another dip or an eclipse. So that's for eclipse in binaries, but we can use this method to study black holes that are hiding with other stars. So it's like playing hide and seek with these systems. So again, light curves are the technique that we use for photometric variability, brightness versus time. Okay, so I won't go through all of this, but I will talk about two different kinds, to actually find black holes. So one kind is this ellipsoidal variability method, and then the microlensing method. So I'm going to talk about that next. Okay, so what is the ellipsoidal variability method? So the ellipsoidal variability method is because of the gravity of the black hole, the star is distorted. The star becomes like a usual star is like a circle, but because of the black hole, it becomes like a teardrop, or like it's very distorted. It's not like a sphere, not like a circle. So it creates this teardrop like shape, and if we monitor the star for a long time, we can see that the light changes because of this distortion of the black hole on the star. So that's the method for ellipsoidal variability. The microlensing method, which is even cooler and like much more awesome, but it's very hard to do, is essentially this. So you have a lot of stars in the Milky Way, and then there are some rogue black holes. So these black holes are not on binary orbits, but they're just going across the Milky Way. They're not tied to anything. They're like like people who are just just roaming about in like cargills or something. It's just they are going in front of stars all the time, but because of general relativity, when it goes in front of a star, so you have the background star and the lens. So what happens is that the black hole or the object, it bends light like a lens. So it bends the light instead of the light going in straight lines, it goes through curved lines, and that amplifies the light. Like a lens, it really amplifies the light. So you have the brightness versus time. When the black hole goes in front of the star, they're not in a binary orbit, but like it's like a lens moving across you. It amplifies the light, and then we can study this bump, this curve, to calculate the size of the black hole and where it is, things like that. That's the microlensing method. It's based on general relativity and how light bends when there's something lensing it. Okay, so now I'll talk to you about Assassin, because we use this survey to do the photometric variability method to try and study the light differences because of black holes. Okay, so the sky is very big. How big is the sky? So there are about, you can calculate this, and you can see that there are about 41,000 square degrees in the entire sky, both from the northern part and the southern part. From Sri Lanka, you can only see a little bit of the sky. You can't see all of it. So like if you go to the South Pole, you can only see the southern part. If you go to the North Pole, you can see the northern part. So then you can calculate this into something called arc seconds. Arc seconds is about 1 divided by 3,600 degrees. And if we want to have a detector with a pixel with about 1 arc second, it will take us 1 terabyte to actually record the entire sky in one snapshot, if you want to do this with 1 arc second pixels. So if you want to image the entire sky, it's 1 terabyte. That's a lot of data. Like imagine doing this every day, 1 terabyte every day, it'll add up. So usually telescopes don't have 1 arc second pixels. It's bigger than that. Like Assassin is about 8 arc seconds. So the data rate is about a few gigabytes. So we can actually collect the data over long periods of time. So these are the Assassin telescopes. We actually use Nikon lenses. These are, you can buy it for your DSLR cameras also. But what we do is we buy them and then we fix them onto a nice mount. And we buy CCD cameras and attach the Nikon lenses to that mount. So it's much cheaper to build these telescopes than building an actual big telescope. This one would take about, a few tens of thousands of dollars, which is still expensive, but compared to other telescopes, it's cheap. So you build these telescopes and then you put them all over the world, and then you let them run. So these are robotic. So we are automating all of this. So we don't have to actually go there and take the data ourselves. We write a script and code it. So there's a lot of coding involved, software programming, and you make the telescopes observe the sky automatically. So very little effort on our part, except for processing the data. So we get about 6,000 images every night. And we can actually see a lot of stars. There are about 100 million stars in the ASASSIN data. But another important point is about how telescopes look at stars. So we have to use things called filters. So we don't have to get all of the light, but we only want some of the light. So we can study light in one part of the spectrum. So ASASSIN uses a G-band filter. And in green, I've shown you what our eyes can see. So it's optical light. So ASASSIN will see things like our eyes would see, but except much stronger, because our eyes can't see as faint as ASASSIN. Okay, so this is what ASASSIN does. We have monitored the entire sky thousands of times from these robotic telescopes, and we take pictures over many years, since 2014. But now I will tell you how ASASSIN data processing works. So this is a picture of the Large Magellanic Cloud. You can't see it from Sri Lanka. You have to go like more south, like Australia or South Africa, to see this. So the Large Magellanic Cloud is a dwarf galaxy that orbits the Milky Way. So this is the ASASSIN reference image. So we build this by taking data and add it up. You add the data up over many years, average it out, and then you have this reference image. So we build this over many years. We have this reference image, and then we get a new image. Let's say tonight, we get a new image of the Large Magellanic Cloud tonight. And then what we do is we use something called image subtraction. So you take the new image and then you subtract the reference image. So it's like A minus B. And then what you will get in the end is this thing called a subtracted image. So each of these dots, each of these pixels tells us about changes. So here, white means there's more light in the new image than the reference image. Black means that light decreased. So this is a technique that we use, image subtraction. And this is how ASASSIN uses the technique to find supernova in the local universe. So we collect data and then you find supernova. So basically there are like few million detections every night, millions of detections, but we can't look at all of them. So we have to use machine learning. Machine learning removes many of the unnecessary detections. And then you have about 200 to 500 actual detections every night. So what we do is we actually look at this every detection by eye. We go through it by eye to verify it, to see if there's a supernova in the image. So this image shows the detection of the most brightest supernova ever known. We found it with ASASSIN. It's called ASASSIN 15LH, and it's barely visible in the data. That's because we try to find it before it becomes very bright and announce it to the world. Okay, so once you find supernova, you actually have to use other telescopes all over the world to get more data. That is what we call follow-up. So this is what we use for black hole searches too. We have to use more than one telescope to get data. So quick summary of what I did before. I worked on classifying variable stars. Took the data from ASASSIN to find things that change over time, brightness changes over time. We found 220,000 new variable stars. which was a big addition to this field. And we also found a lot of ellipsoidal variables. These are the ones I talked about before. These could have black holes in them. So we have about 370 ellipsoidal variables. Now what we're doing is trying to get more data from more telescopes to study and see if there are black holes hiding in these systems. So yeah, ellipsoidal variability is one of the easier methods to do this. So Khalid asked me to talk about some cutting edge results too. So I will talk to you about some of the latest discoveries of black holes in the Milky Way. So one of the black holes that we have called Auriga. This is based on the constellation Auriga. It's a charioteer. This nice picture shows you the constellation. And this was data that we published in 2019, where we found a black hole in the Milky Way. So how did we find this black hole? So this black hole is around a red giant. So as I told you before, red giants are when stars like our sun become older, they grow and become red giants. And we looked at the photometric, the light curve data in Assassin, and then it was varying, but it was not varying because of ellipsoidal variability. So we were able to estimate the K, the amplitude that I mentioned before. So I will tell you how we actually used those two techniques to do this kind of discovery. Okay, so this is the data. This is the actual data for this system. So you have the radial velocity from the Doppler spectroscopy method I told you about, and then you have the photometric data from the photometric method. So you use both methods here to find this black hole. So what happens is that the star is moving around the black hole, and that shows up in the Doppler data. And we can calculate the amplitude from this sine curve. We calculated the amplitude, and then from the light curves, what we found out was that the star is actually spotted. So like the sun has sunspots, this star has star spots. So it covers part of the sun, part of the star in a dark spot. So that causes this variation in light. Okay, so we have this K amplitude. This K amplitude is very important because that tells us about the mass of the black hole. So we looked at the K amplitude and we calculated the mass of the black hole. So what we get is that this is a binary system with a red giant and a black hole. The binary moves around in 83 days. And the mass of the black hole is about 3 times the mass of the sun. So it's a very small black hole. It's a small stellar mass black hole. We have nicknamed them baby black holes because they're not as big as the ones that are found by LIGO, for example. So this was one of the latest discoveries that we did. And this really showed us that we can use this Doppler spectroscopy method and the photometric variability method to find black holes. This was a very important piece of work. So yeah, that was the summary of that discovery. And the latest discovery that I worked on in January this year was the unicorn black hole. So this is the closest black hole to the Earth. This is the closest black hole to the Earth, and it's about 1,500 light years from the solar system. So we can't, it's not a danger to us, but it's kind of far away. But compared to other black holes in the Milky Way, this is the closest one that we've found so far. And also, it is the smallest black hole that we've found so far. So it's the closest and the smallest. And this unicorn black hole is what we call another baby black hole. So how did we find this? So this is also a binary red giant plus black hole. And the cool part about this is a very bright star. If you have binoculars, you can actually observe this. So you can take a binoculars and look at the star. It's very bright. So The Doppler spectroscopy method was used many years ago to calculate the K amplitude of this star, but people thought it was eclipsing binary, like the one where you have two stars, red giant plus another star. So they did not talk about it much. But what we did a reanalysis of the system. We went and looked at the system again. We got the data from the photometry method. We got light curves in different filters, and these are the light curves. And what you can see here is that you can see the ellipsoidal variability that I mentioned. You can see the star. If you look at this plot, you can see the star being distorted into a different shape, not a circle, and that creates a signal like a sine curve again in the light curves. So what you can do, this is a method that has been, people have been using this method a long time to find exoplanets, other stars, but you can model the light curves. You can, there's software to actually take a model and fit the data. So it's like fitting a line, but you actually have a model for the system. So we fit a model with a red giant and a black hole, and we can get the information about this system from the model. So we have, we get the mass of the giant and the black hole from modeling. That is, and we use data from Doppler spectroscopy method and the photometry method. Okay, so this is where we put our discovery in this important plot that I told you about. So it falls in this gap. So there's a gap between neutron stars and black holes, and we haven't found a lot of black holes in the mass gap yet, but we are finding them more and more now through the new techniques that I talked about today. So yeah, this is our unicorn black hole is in the mass gap. So again, there was a nice video about this, and I will recommend you to take a look at it. It's called the largest black hole in the universe size comparison. So you can look at it and see it has nice animations that show the size of the different black holes that we know of. And it goes on until the biggest black hole that we've ever discovered, the supermassive black hole. So this is an illustration of the unicorn black hole here. And they put it in the video, which is really nice. So we published this, and then it became a news story. It was in National Geography, Reuters. It was the closest black hole, so people were very excited about it. And yeah, so it's very close, 1,500 light years or 460 parsecs. And it's a baby black hole again. So what is next for the field? So what is next is, again, we have to go and analyze a lot of data. So that is where, a lot of people are coming together now to use the Doppler spectroscopy method and the photometry method. This telescope that I'm showing here, the Vera Rubin Observatory, it will be one of the biggest telescopes ever built. It's in Chile. They're building it right now. It will record and observe the southern part of the sky every night, and it will create about 1 petabyte of data every day. It is kind of crazy. It's a huge telescope. They're building it, and that will have so much data for the photometry method that we can use. And then Assassin will keep running. We'll get data. And then you have NASA TESS. It's a space observatory that also uses the photometry method. And then another upcoming NASA telescope called Roman Space Telescope to actually, go in and get data. And this is where I think a lot of effort can come from Sri Lanka too, because there's a lot of things that we can do. Because the data is available, you need to just get it and analyze it, and we can make a big impact, because there's a lot of really good people there. Like I know that University of Mora tour, there are very good people who know how to do this. It's just fitting models, getting data, analyzing it, and once you have that, you can do a lot of things to find black holes. So the future is very bright, and I think or just like finding exoplanets, we'll keep finding so many more. And if we have the resources, Sri Lanka can make a big impact on this. And I think we can do so much. So there are many black holes that are in the Milky Way. 100 million black holes are there in the Milky Way. We haven't found even a little bit of them so far. The amount of black holes we know of in the Milky Way is about 50 black holes. So yeah, I think I will end my part of the talk and I will now take questions. So thank you so much for listening. Again, I'm very sorry I couldn't explain all of this in Sinhala because I learned all of this in English. It's kind of hard for me to explain in Sinhala, but I will try to answer your questions to the best of my ability. So thank you so much.